Are you dealing with a misfire or other drivability concern, code or no code? Well, there are only 4 possibilities you need to consider. Hi, I'm Pete Meyer, and this is Cardone ProTech. The Cardone ProTech series is produced in partnership with Motor Age, America's oldest trade publication for the automotive professional. When you find yourself dealing with an engine drivability or performance issue, finding and isolating the cause can seem a bit daunting. That is until you remember there are only 2 areas that you need to focus on. The first is using a consistent diagnostic process, and second is understanding that there's only 4 fundamental areas that could cause such a problem. What are those 4 fundamental areas? The first is engine mechanical condition, specifically the engine's ability to compress the air charge and seal the combustion chamber. The second is the engine's ability to breathe, also referred to as volumetric efficiency, and encompasses any condition that prevents air getting in and out of the cylinders. The third is ignition, on a gasoline engine anyway. This covers everything about delivering a strong spark at the right time. And the fourth is fuel. This covers not only fuel delivery, but proper fuel mixture, delivered cleanly and at the right time through the injectors into the combustion chamber. So let's apply this to a common customer concern, misfires. Whether there's a DTC set and the check engine light is on, or it's just something you can feel in the seat of your pants, misfires can be a real problem. They damage the catalytic converter, increase emissions, and reduce fuel economy. Now, we can isolate the cause of this if we follow the second half of what I talked about at the beginning, and that's following a logical diagnostic process, one that you apply to each and every troubleshooting situation that you come across. It's key to follow the same process because it removes that as a variable when you're trying to isolate and find the cause of your customer's concern. It also helps you speed up your diagnostic process, makes you more efficient and more accurate. I like to compare it to being a detective. Before an arrest is made, a lot of research and investigation goes into the process, and at the beginning, everyone is suspect. The same applies here. Never assume that a system or component can't be part of the problem. Oftentimes, if you do, you'll find yourself going down that rabbit hole that Alice went down, spending hours troubleshooting something that turns out to be exactly what you thought at the beginning it couldn't be. Write this quote from Sherlock Holmes down and pin it to your toolbox as a reminder. When you have eliminated all which is impossible, then whatever remains, however improbable, must be the truth. Our process begins by interrogating the victim, in this case, the engine control module. After all, it was the ECM that turned on the check engine light to warn us that a crime had been committed in the first place. But don't immediately jump up and grab the factory scan tool, or even use the enhanced mode of your favorite aftermarket scan tool. Instead, select generic or global OBD2. There are a few reasons why I recommend this. First, it doesn't matter where the vehicle was made. If it's for sale in the United States, it has to meet global OBD2 standards, which means for us, no matter what the brand, if the customer brings you a vehicle with a check engine light illuminated, you should be able to access the information you need to correct that problem. Second, there are 10 modes, tools if you will, as part of the global OBD2 standard. We're going to cover those as we go along today, but right now I want you to understand that these are valuable resources that will help you make an effective and accurate diagnosis. And third, the data that you see in the live data stream has to be accurate. What do I mean by that? Well, in some OEMs, if you look at the enhanced data, if there's a problem with the sensor or system, they may tell the ECM to use a substitute value in place of what the sensor is actually reporting, so the vehicle is drivable and the customer can get it to the closest service facility. But when you look at that data on your enhanced scan tool, you're going to see the substitute value, and you may go right by the problem and not even know it. Today, I'm using the Automotive Test Solutions eScan, a global OBD2 scan tool with additional features that will help speed up my diagnostic process. Let's start by using Mode 3. This is where the DTCs that cause the ECM to turn on the mill are kept. Take a snapshot or write them down before moving on. And don't clear the codes using Mode 4 when you've just accessed Mode 3. You're going to wipe out some valuable diagnostic information you haven't even taken a look at yet. The next stop is Mode 7. This is where you'll find the pending codes, the ones the ECM is keeping an eye on but hasn't yet moved to Mode 3. They can often provide clues on which of the 4 pillars I told you about that we may want to tackle first. After Mode 7 is Mode 10. Any codes here are referred to as permanent codes and cannot be cleared by anyone or anything except the ECM. Mode 4 won't do it, a battery disconnect won't do it, even clearing Keep Alive memory won't do it. And that brings me to another important point. When you're trying to correct the cause of a check engine light or DTC, your customer is actually the ECM or engine control module. If your repair doesn't meet the test requirements that the ECM is going to use to test that system for itself, well, guess what? That check engine light's just going to come right back on again. I still have one more thing to check, and that's Mode 2, or freeze frame. Imagine for a moment that at the instant a crime occurred, a photographer was there snapping pictures. How helpful would that be to the detectives? And that's essentially what freeze frame is. It's a snapshot of the operating conditions the vehicle was under at the time the ECM decided to turn on the check engine light. It's important especially when diagnosing any code related to a continuous monitor, specifically misfires or fuel trim related issues. There are a few other modes in Global OBD2 that I may want to take a look at later, but right now I think I have the foundation of information I need to proceed. Now it's time to do a little homework. Now, I want to make a point here. The vehicles that are coming into your shops today are the most highly complex, highly technical marvels of automotive engineering that the automakers have ever produced. And unlike the good old days, they don't go along real well with repairs that are close enough. Today, the vehicles that you're servicing, you either fix it right or you fixed it wrong. That's why taking the time to read up on the code and the systems you're working on is critical to your success. Today, even routine tasks like changing a battery require very specific processes that must be completed before you call it finished. If you take the time now to do your homework, you'll find that your time spent testing and repairing will be less, and you'll be a more accurate and efficient diagnostician. After doing just a little bit of homework, I learned very quickly that a misfire is defined as a lack of combustion in the cylinder, and it can be caused by a variety of factors. So I have to wonder, why is it that ignition coils and spark plugs seem to be the first thing that technicians throw at the problem to see if that will fix it? Can you say, a parts changer? As a diagnostician, I want to know, what is it that the ECM is looking for to determine that a cylinder is misfired? If I understand that, I can use that information in my own troubleshooting. Now, in the case of this vehicle, as most others, the CKP or crankshaft position sensor is the main source of information to the ECM when determining whether or not a misfire has happened. The input signal generated by the CKP sensor is derived by sensing the passage of teeth from the crankshaft position wheel mounted on the end of the crankshaft. And that signal is then used to calculate the time between CKP edges and the crankshaft rotational velocity and acceleration. By comparing the acceleration of each cylinder event, the power loss of each cylinder is determined. When the power loss of a particular cylinder is sufficiently less than a calibrated value and other criteria are met, then the suspect cylinder is determined to have misfired. Well, that lines up with the definition of misfire, doesn't it? That means that I have to consider any factor that could affect a cylinder's ability to contribute its fair share of power. There's a lot more information regarding this monitor and DTC in my service information, but in the interest of time, I'm not going to go over every bit of it. But before I leave the desktop, there is one more thing to make sure we check for, and that's technical service bulletins. Everything that ECM sees and does is controlled by its programming. And when the vehicle was new, the programming it contained may not quite fit the realities of the real world. When that happens, the software engineers may issue an update to that programming that has to be programmed or reflashed into the module. Sometimes it's a parts problem, and the factory issues a new component to take its place. A great example is related to the 2005-2006 Ford Escape. Codes were being set related to the drivers for the coil-on plug ignition system that were found to be ultimately caused by the original coil design. Problem is, you wouldn't know that if you didn't look for the TSB. The bad coils were burning out the drivers in the ECM, and this is the part that technicians were replacing. The only problem was they hadn't read the TSB, so the bad coils didn't take very long to burn out the new ECM. Now, the method I showed you for checking all the actuators in our last video may or may not have discovered that problem, but I can promise you one thing. If you had done your homework and read the TSBs, your fix would only have to have been done once. With what we now know, we can start our diagnosis. We understand that a misfire can be caused by any factor that contributes to a loss of power in any given cylinder. And that means that all the four pillar areas that I explained at the very beginning are all potential suspects. That is, until proven otherwise. What do you say we start eliminating some suspects? Now, in addition to the eScan scan tool, I'm going to be using the ATS eScope to help me in this diagnosis. More and more technicians are realizing that a good digital storage oscilloscope can really help them in their diagnostic process. And the very first test that I want to make is a perfect example of that. Remember the four pillars? Well, the first one I'm going to tackle and check is general engine mechanical condition. That is the engine's ability to seal and compress. And I'm going to do that with what's called a relative compression test. To keep it simple, the test uses the work that the starter motor performs when cranking the engine. If the engine is tight, that is, all the cylinders have good compression, the starter motor has to work that much harder. The increase in current draw creates an increase in voltage drop at the battery, and that's something that I can measure with the eScope. We'll connect to the vehicle per the scope's instructions. It's a simple attachment to the battery, and the scope will trace the drops in voltage caused by the peaks in current demand from the starter. It will also populate an easy-to-read bar graph and help me quickly identify any weak cylinders. And while there are some limitations to this testing method, traditional testing methods are not going to do any better. The test passed, so I'm 95% sure that a mechanical sealing or compression condition is not what's contributing to the misfire. If I wanted to take a look more accurately and more deeply, I can use what's called an in-cylinder pressure test, which uses a pressure transducer installed in place of the spark plug to physically measure and monitor the pressure through the entire 720-degree cycle of the engine in the cylinder that it's connected to. Here's what a scope capture might look like using this technique. I can easily see the compression pressures in this running engine and identify when the valves are opening and closing. And there's a lot more to this one single pattern than we really have time to cover today. But let me know in the video comments if you want to see more about this particular technique. The next pillar we're going to tackle is checking the engine's ability to breathe. Now, there are a number of factors that can affect that ability. Clogged air filter, cam timing out of specification, VVT actuators that are not functioning properly, even a clogged catalytic converter can all impact the engine's ability to move air in and out of the cylinder. Now, if this test passes, I can eliminate all of those possibilities as contributors to the misfire I'm trying to correct. The E-scan will help me with this test, but it's not truly needed. You can do this test with any scan tool on any vehicle equipped with a mass airflow sensor if you know what data PIDs you need to track. And after your test run, you'll need to enter them into a VE calculator back at the shop. One down and dirty method for quickly checking volumetric efficiency is to monitor the absolute load PID on the live data stream. But no matter which method you decide to use, you're going to have to perform a test run in order to collect the information. Find a test area near your shop where this is safe and responsible to do this kind of a test. In fact, establish a test route that you use for every car that comes into your shop. Again, to eliminate the variables that changing the route might cause in your troubleshooting process. For this particular test, we're going to find a safe area to start off in a rolling first gear start, and then we're going to floor it. We're going to push the throttle pedal all the way to the floor, and we're going to keep it there until we make that second gear shift, all the while recording the data PIDs we need to determine volumetric efficiency. In the case of our VE test, the red in the graph indicates the theoretical volumetric efficiency of the engine, while the yellow indicates the actual volumetric efficiency of the engine. If these two don't line up, it indicates a problem. But since we have a passing grade on our test, I can eliminate a lot more suspects, and my pool of potential causes is getting smaller and smaller. So on to number 3, ignition. Now, when I'm checking the ignition system, I really want to know two things. First, is the spark strong enough to light off that air-fuel mixture? And number 2, is it happening when it's supposed to? Well, the first is easy enough to test with a very basic tool, and that's a spark tester like this one. All I'm going to do here is increase the gap in the tool to really stress the coil to its max. And if it can jump that kind of a gap, it can certainly handle what's going on inside the combustion chamber. The other may seem a bit more difficult. After all, there are no timing marks anymore for me to use like we had way back when. But I can still do it, and I'll do it using the same technique I used for the relative compression test. Only this time, I'll add another channel to an ignition source and use that as my reference. This is a sample of what I mean. See how the ignition event is nearly centered on the current peak shown here? And where does that peak occur? TDC of the compression stroke, right? Isn't that when the spark plug is supposed to fire, just before TDC compression? Now, if the two patterns are way out of alignment, well, that's where I need to narrow down and start doing some pinpoint testing to determine the reason why. A couple of reasons pop immediately to mind. Perhaps the keyway for the timing gear on the crankshaft has sheared, allowing that gear to shift out of sync with the crankshaft itself. Maybe there's a problem with the reluctor wheel that the crankshaft position sensor uses to trigger. Might even be a problem with an individual coil itself. All I know is that now I'm narrowing down on a possible cause, and I need to explore that further using those pinpoint tests. Now on to our last pillar, fuel. Fuel is often something I save for last because it's very possible to have a single injector that has an issue, and it can be very difficult to determine that. I like to think of fuel in terms of the quantity, the weight of fuel that's actually getting into the engine. You know, we all know what stoichiometry means, right? It's the 14.7 to 1 ratio of air to fuel by weight. Pressure is important, yes. Volume is important, yes. But those are the means that we use to get that weight of fuel, the right amount of fuel, into that combustion chamber. The ECM knows how much fuel the injector will flow at a specific pressure and adjusts the on time of the injector accordingly on a port injected engine. GDI, though, is totally different and more like a diesel common rail than a port injected gas engine. In these systems, the fuel isn't added until just before the piston reaches TDC on its compression stroke, which means we have very little time, only a few milliseconds, to get all the fuel we need in the combustion chamber. In these designs, pressure is raised to meet higher fuel demand instead of pulse width. Now, while testing the low pressure side of a GDI equipped vehicle is the same as you're always used to doing using your mechanical pressure gauge, because of the high pressures involved, you can't use that method to test the high side of the system. You're forced to rely on the scan tool data that the ECM is supplying via the fuel pressure regulator sensor on the fuel rail. Now, the only problem with that is sometimes scan data lies, and it can also be difficult for the ECM to pick up on an injector that's not performing as it should. Well, in the old days, we used to perform what's called an injector balance test, but again, the high pressure side limits how we can do that. Or does it? I can use my scope, and I can do this test in one of two ways. I can either tap into the signal wire from the fuel rail pressure sensor and use the same information that the ECM is using, or if possible, I can tap into the fuel rail itself, just like you would with a mechanical pressure gauge, but instead installing a pressure sensor or transducer to see what the drops look like on my scope screen. Here's an example of what that would look like. Another technique that you can use is to look at fuel trims. If the engine has a misfire related to ignition, that is weak or no spark, the air-fuel mixture going into the combustion chamber is still correct. And as it passes through the exhaust, the heat of the exhaust is still going to allow it to combine. And by the time it reaches that upstream oxygen sensor, well, the sensor is going to think that everything is just fine in terms of mixture and let the ECM know the same. So you'll see very little, if any, change in the fuel trims. Conversely, if there's a problem with fuel, not enough being added, for example, or too much being added, that's going to affect the air-fuel ratio, whether it combusts completely in the cylinder or in the exhaust stream. And that is something the oxygen sensor will react to and cause those mixtures to adjust accordingly. The techniques that I've shown you so far should help you isolate the possible causes of about 95% of the concerns you might have to face when dealing with a drivability complaint. But there's always that 5%, right? The 5% that are a little harder to isolate and correct. Another technique that can help is monitoring the secondary ignition pattern, showing the spark traveling across the plug gap, also known as the burn line. This too has a wealth of information to share with the trained professional, and the ability of today's scopes to record data over an extended time allows this resource to be collected and reviewed, looking for the odd man out. But as you continue to develop your professional skill sets through education and training, you'll learn some advanced techniques that will help you isolate and locate the problem on these harder cases. Always remember though, use the things that God gave you first. Your mind, your sense of touch, smell, hearing. All of these help contribute to growing the most important resource you have, the ability to critically think and apply knowledge to a new situation. It's a knowledge you've been honing your entire professional career. You may not even know that yet, but I'm going to let you know that this will serve you well, not just in taking care of your customers, but in taking care of yourself and your family. Well, that's going to do it for today's Cardone Pro Check. I'm Pete Meyer. Thanks for watching.